And here's the exercise. This is actually a pretty important little exercise. Suppose you've got a standard normal random variable. You know, we usually call that Z, right? Z is the standard letter for standard normal random variable. Normal with a mean of 0 and a variance and standard deviation of 1. Our book always, well, in all books, typically call that first number the mean, mu. Our book calls the second number the variance, sigma squared. You should be aware that other books label that as the standard deviation. However, when it's 1, it doesn't matter. The variance and the standard deviation are the same when they're both 1. What I want to show, well, okay, instead of showing something, let's explore or ask a question. What is the distribution of Z squared? So Z has a standard normal distribution, a standard normal random variable. Its PDF, its density, is a bell-shaped curve. Centered at 0 with a standard deviation and variance of 1. And I hope you remember that means the inflection points of this graph are 1 unit away from the mean, so that we'd be at plus or minus 1. You'd also have things like the 68, 95, 99.7 rule. 68% of the area is between -1 and 1. 95% of the area approximately is between -2 and 2, within 2 standard deviations of the mean. About 99.7% is within 3 standard deviations of the mean, between -3 and 3. What are we doing when we say consider Z squared? Are we like squaring this PDF or something? No. You're imagining squaring the outcomes of the random variable Z. What does that mean? Well, think about it. If this is modeling data, the fact that the density is highest near 0 means the majority of your data would be clustered close to 0. In fact, about 68% of it will be between -1 and 1. About 95% will be between -2 and 2, etc. But the higher the PDF is, the higher the density is, the more dense your data will be. Of course, to really see dense data points, you'd have to have lots of them, probably like thousands of data points or something like that, to really see the density. If you made a histogram for these data, a bar chart, it should have this kind of shape. It should be densest, the highest frequency near 0. It's those values you need to imagine getting squared. Now, those values are both positive and negative. When you square them, you're not going to get a negative number, right? No imaginary numbers here. So whatever the distribution of Z squared is, it can't take on negative values. And since the majority of the data is close to 0, like between -1 and 1, when you square them, those numbers are still close to 0. In fact, between 0 and 1. So whatever the distribution of Z squared is, it should have a density that's positive, not negative. It's going to take on values of 0 when the input is negative. Relatively high between 0 and 1, and relatively low greater than 1. Does it do something like this? I'm not going to actually draw it yet. Does it do something like this, perhaps? Or does it do something like this, perhaps? That's not so clear. See what I just did? Does it do something like this? Or does it do something like that? That's not so clear. Let's see if we can figure it out. How? Well, let's give this quantity a name. Let's call it Y. turns out to be easiest in determining the distribution of y to find its CDF first instead of its PDF. CDF of y is an easier thing to figure out. What should I call it? Well, how about capital F? Maybe capital F sub y, sub capital Y of little y. Why are we doing this? Well, for one thing, it's of theoretical importance. For another thing, it's going to lead us towards simulation, actually, with another example. The CDF, remember, I did mention this last Thursday, is always the probability that the given random variable is less than or equal to the given value. It's always the case, whether your random variable is discrete, continuous, or mixed. Some mixture of discrete and continuous. We're not going to talk about mixture today, but we probably will on Thursday. This is always true. The way you compute it is different, depending on whether it's discrete, continuous, or mixed. If it's discrete, you compute this as a summation. If it's continuous, you compute this as an integral. And if it's mixed, well, that's not so clear at the moment. Maybe some sort of combination of summations and integrals, maybe. I'm not going to actually compute it as an integral here. I'd like to think about it theoretically. What should I do? Well, I better use what I'm assuming somehow, right? I'm assuming z is standard normal. I better use that. How? Well, I'm saying y equals z squared, so go ahead and replace y with z squared. Z is standard normal. How can I relate this now to z itself, not z squared? What do you think I should do? Got a guess? Take the square root. However, in taking the square root, you do have to be careful. Z can take on positive or negative values. Z is standard normal. To say z squared is less than or equal to little y, where little y is greater than or equal to 0 here, is really to say that z itself is between negative square root of y and positive square root of y. Right? If z squared is less than or equal to 4, that means z itself is between -2 and +2. If z squared is less than or equal to 9, then z itself is between -3 and +3. All right. So now should I go like to a standard normal table or something? Tell me solve this? Well, you could if you knew what y was, but y is a variable here, so it's not so clear. I could use the symmetry of the normal curve about 0 to say this is 2 times the probability that z is between 0 and square root of y. That would be symmetry by symmetry. And that makes it a little easier to think about, perhaps. Perhaps. Actually, yeah, that'll be a little easier. Let me write the CDF of z in its actual usual form that people use outside of our textbook. The CDF of standard normal random variable, I think I mentioned this last Thursday, is typically written as capital phi. That's the standard notation for the standard normal random variables CDF. And the probability that z is between 0 and square root of y can be written as the difference of CDF values, right? Why does that work? Well, intuitively it works because you're thinking of the area under the graph from 0 to square root of y, this area right there. You're thinking of it as the area under the graph to the left of square root of y forever, minus the area under the graph to the left of 0 forever. And actually, by symmetry, this is 0.5. I know that's 0.5. So ultimately, we can actually write this as 2 times capital phi of square root of y minus 2 times 0.5 is 1. I could write ultimately the CDF of capital Y in terms of the CDF of a standard normal. Capital phi is the CDF of standard normal. That is standard notation that many, many people use, many books use. So I could write the CDF of Y like that. Is that helpful? Do I know the formula for the CDF of standard normal? That involves ERF. Remember ERF? Error function. It's not an elementary function, not a function you're used to. The new function. So I can't really simplify this anymore, it seems, without using ERF. However, I do know the formula for the PDF of a standard normal. Right? It's in chapter 4, it's in the table. It involves E. By the way, exp essentially means E to the whatever that is. Just shorthand. Actually, it's not really shorthand, it's typographical. Typographical reasons they put an exp there. So that when you got this, if you wrote it as E to this humongous power, then it gets hard typesetting wise. So exp of something means E to that something. Exp stands for exponential function. That's the PDF. And if mu is 0 and sigma is 1, it simplifies a lot. So, maybe I should try to find the PDF of Y now. Maybe I should differentiate this. This is a pretty important technique that I'm showing you here, including for applications, including for simulation. Little f sub capital Y of little y, the PDF of capital Y, by definition in the continuous case, is the derivative. Because this is a continuous random variable of capital F. I forgot to put a prime in there at first, now it's there. Capital F sub Y prime of little y. So differentiate this thing. I got a square root of y in there. I guess I need the chain rule. -1 differentiates to 0, so that's not a big deal. The 2 stays there. 2 times the derivative of capital phi evaluated at square root of y. Then by the chain rule, what's the derivative of square root of y? 1/2 y to the negative 1/2. The 2's cancel actually, and you're left with capital phi prime of square root of y divided by square root of y. Capital phi prime, though, is this function when mu is 0 and sigma is 1. Let's write it as e to a power. I'll bring this 1 over square root of y out in front. 1 over square root of y times, from the table, it's 1 over square root of 2 pi e to the negative x minus 0 squared, which would be just negative x squared. Or, excuse me, sorry, mistake. Scratch that out. 1 over square root of y times 1 over square root of 2 pi e to the negative, yes, x squared if the variable were x, but I'm replacing x with square root of y. So it's square root of y squared over 2 sigma squared. And sigma is 1. So this is a PDF of y. Y is positive here. Remember, initially I said y is greater than or equal to 0, though remember with continuous random variables, it doesn't matter whether you use strict inequalities or non-strict. Here it kind of made sense to say y could be 0, but with this formula, y can't be 0. Is it really a PDF? We should probably check it with Mathematica. Do that up here. It should integrate to 1, right? Zero to infinity. 1 over, I guess I could do all the square roots together here. 2 pi times y e to the, use a capital E, negative square, okay, I could simplify it a little bit. This would be negative y, square root of y squared would be y. Negative y over 2. 1, yay. Yeah, it simplifies a little bit. And in fact, I'm even going to rewrite it a little differently. Actually, rewrite it even differently. 1 over square root of pi. I'm going to write the square root of 2 as 2 to the 1/2 separately like this. And I'm going to write 1 over square root of y as y to the negative 1/2. And then I will simplify the exponent there to be e to the negative y over 2. Why did I do that? Because this is actually a familiar PDF. I'm sure you didn't memorize it, but it is actually in our friendly table, our friendly neighborhood table. Same table, chapter 4. This function right here is, can't get them all on this, okay. Is the same as, or at least very similar to this function, chi squared. Can you see it? Is that big enough? You can look in your book if you like. Page 136. Right there. Except a y instead of an x. We got an e to the negative y over 2. We got a y to the negative 1/2. That's going to fit this pattern if the little gamma is what? 1. 1/2 minus 1 would be negative 1/2. We got to divide by 2 to the 1 over 2, 2 to the 1/2, square root of 2. Oh, does that mess things up? Capital gamma of 1/2. Is it square root of pi? Mathematica, what is capital gamma of 1/2? Square root of pi. Yeah. Wait a minute. Isn't the gamma function the factorial function? Gamma of 6 is 5 factorial. Gamma of 7 is 6 factorial. Remember that? What? How could you gamma of 1/2? What is that? Negative 1/2 factorial? Can Mathematica even do that? I guess so. What? The gamma function is defined for other values of the input besides positive integers. And it can give you weird things like this. It's defined in chapter 4 using an integral. A very strange looking integral. Oh, where are we? The capital gamma function is this function of alpha. And I guess you're allowed to plug in alpha equals 1/2 into that, and I guess you would get the square root of pi for that integral if you did. It's not clear why. You could look into it if you're interested. We're trusting Mathematica here. We have a chi-squared random variable here with little gamma 1 degree of freedom. Little gamma was the degrees of freedom. That's what this is. That's the result. What is the distribution of z squared? It's chi-squared with 1 degree of freedom. That's what it is. And that's actually important for us in this class to know that. If you square a standard normal random variable, the result is a chi-squared random variable with 1 degree of freedom. So our result here, and Dr. Wetzel like to use to call these things results rather than theorems, because we're not really being careful in how we state these things. Result, if z is standard normal, that implies z squared, I guess you could write it like this, is chi-squared with 1 degree of freedom. That's not an x there, that's a Greek letter chi. It, of course, looks like an x, but we call it chi. I was always used to calling it chi-squared, but many people call it chi-square. Why? I looked it up. It's because you're not literally squaring anything with this. You are squaring that. Maybe that's the origin of the name, but you're not literally squaring the symbol. So for that reason, some people call it chi-square. I always learned when I was younger, chi-squared. It's not a big deal.